So let's begin. Eugene is also here, but it's good to have Norm give us a longer, not larger, a longer version of the second lecture. So, Norm.
Sounds great. Yeah. Thanks again, everyone, for suffering through the extra lecture since I was too sick on the first couple of days. I apologize for that, but hopefully you guys have been learning and enjoying this. Okay, so I'm going to jump right in since the first lecture was not that long ago, just yesterday. I'll start with a just very, very short recap, and then we'll jump right in. The first recap is that I was a little bit remiss. It was pointed out to me that towards the end of the last lecture, when we were sort of trying to figure out, is there any pure quantum state that can saturate the quantum Kramer-Rao bound? And the idea, I think Dr. Machado helped us answer that indeed the cat state, that's a superposition of the max and min eigenvalues, would saturate the variance that we were looking for. And then when I went back to our very classic example of n spins and the collective spin operator sigma z total, I forgot, of course, to mention that the state that you get out, which is a superposition of the configuration that has the maximum eigenvalue of n over 2 and the minimum eigenvalue of negative n over 2 for such n spins, is, as all of you I'm sure know, commonly referred to as the GHZ state. Usually written as just all down plus all up over square root of 2. And I want to emphasize that this will be the first kind of shining example that we'll try to understand in a little bit more breadth as we continue. Okay, just a recollection that I didn't talk about that. The second thing I wanted to emphasize is this perspective that I've been trying to beat into all of you, which is a little bit of a more formal perspective for how to really think about what exactly it means to try to design metrological states and do quantum sensing. And that's that the goal, as you've now seen from the classical Kramer-Rao bound, the classical Kramer-Rao bound in quantum form, the standard quantum limit, and the quantum Kramer-Rao bound, our goal is really at its core, when we're thinking about sensing, to minimize the variance as a function of the number of measurements we perform. We're assuming that we've accurately designed an experiment to be able to detect a signal. And the question is, as a function of the number of measurements that we perform, how do we make sure that we can sense the smallest variation of that? And that means that we want the intrinsic variance associated with the estimator to be as small as possible, oftentimes scaling with the number of measurements that we do n. Good. All right, so let us start by now combining everything together. So we had previously just defined the classical and quantum Kramer-Rao bounds. And so let's combine our Kramer-Rao bounds together. And by combining them together, I claim that it's a very natural way to think about that we now have some integrated variance that you can kind of characterize as being associated with any quantum sensing experiment. Okay. And in particular, when we combine them together, we might say that it's natural to think about the fact that there are two sources of variance in any quantum sensing experiment. The first is what I'll call the classical variance associated with the estimator. And that is really anything that gives you a classical source of uncertainty or a classical source of fluctuation or noise. So let's think about these as classical sources of randomness or fluctuations or errors. So this could be that the variance associated with our quantum sensing experiment, there's really, fluctuations in power, fluctuations in whatever, in frequency, some noise that's very classical. And of course, such sources of fluctuation, the variance associated with them, are fundamentally governed by the classical Kramer-Rao bound. there can be no scaling for delta theta squared that is better than 1 over n, well, c over n. And the second is something that we'll dive into quite a little bit of detail in the beginning of this lecture, which is what I like to call the variance associated with the QSN, or the quantum shot noise. Okay, and I'll define that in just 1 second. Okay, the variance associated with quantum not noise, quantum shot noise. Shot noise. Okay. And the way to think about this is extremely simple. It's extremely simple. All of you know quantum mechanics well. It's really that for any quantum sensing experiment, in the end, we're going to prepare states and we're going to do measurements. And this should be thought about as an additional source of error, because quantum measurements are inherently stochastic. Okay? And I want to say, what I mean by that, for example, you could think about this as just another source of randomness in its own right. Okay? And we don't usually think about this type of randomness when we're talking about classical systems. Hence, quantum shot noise. And I should emphasize that when we think about the variance associated with the quantum shot noise, here there can be, again, two scalings. You might have thought, oh, well, the word quantum sits inside the name here, so it must be governed by the quantum Kramer-Rao bound. But that's not true. It turns out that if you have no entanglement, if you have unentangled degrees of freedom, then you are still governed by the classical Kramer-Rao bound, even for your quantum shot noise. And this, again, I've emphasized, is thought about as the standard quantum limit, but really is just coming from an application of the classical Kramer-Rao bound. And on the other hand, if you do have entanglement, and this is a topic that we will explore in gloriful detail today, if you do have entanglement, then this quantum shot noise can, in fact, be pushed down such that it scales with the Heisenberg limit. And of course, when we talk about the Heisenberg limit, that means that we have gone beyond the classical Kramer-Rao bound, and now we are in the regime of the quantum Kramer-Rao bound, right? So delta theta squared would at best be able to scale as c over n squared. Good. And that very nicely brings us to sort of the second natural part of the lectures. And here in particular, we're going to really unpack in quite a lot of detail how to think about this quantum shot noise, and one entanglement-based strategy to fight against it, which is called spin squeezing. So we'll now discuss quantum shot noise and spin squeezed entanglement. I should ask, actually, are there any questions? I guess it's been very short, but are there any questions on just kind of the tie-up that I've done to sort of our initial discussions on classical quantum Kramer-Raos and things like that?
Yeah, I have a question. So doesn't that imply that you can, the first equation, that you can never go beyond the classical Kramer-Rao bound?
That's right. So at some level, you're saying that, I think you're saying that, if you have these two sources, what does it mean exactly when people talk about, oh, my experiment scales as the quantum, as the Heisenberg limit? It means that you have to put an absolute sorry? Is that is the question, right?
Yes.
Yeah. Okay, good. Yeah. So the point is that quantitatively, you have to push the variance from all your classical sources down sufficiently small so that you are really limited by something that entanglement can help. And that's, I mean, eventually you cannot, you always will have projective measurements. So that's sort of an intrinsic source of noise. But in principle, you can push all of your other classical fluctuations down smaller and smaller. And then when the experiment gets to a certain limit where those projection noise is really going to limit you, that's where entanglement can help you. And that is indeed, for example, where LIGO was. But, you have to go hand in hand. It may be that, at some point in time, your classical noise is too big. You push it down. You are limited by, quantum shot noise. But you push that down. But then again, at some point, you're going to have to hit the limit where you're now fighting the classical noise. So you have to always push them hand in hand down in order to really continue in the Heisenberg scaling. Is that clear?
Yeah.
Excellent. All right, let us continue. Okay, so let us try to unpack. I'm sure you've all thought about this, but hopefully I'll give you a little bit of a different way to think about this. But let us now try to unpack. Let us unpack this shot noise, this concept of quantum shot noise a little bit more. And in particular, let's recall our previous lecture, Ramsey experiment. But since we're now going to talk about many bodies, entanglement, all things like that, but let's just redraw it. But let's just redraw it for n spins instead. And indeed, we kind of already analyzed the n spin case instead, n spin case last time a little bit. And we're going to do so where the n spins are in some product state. So all of the n spins are pointing in the same direction in the Bloch sphere, and that is also known as a coherent spin state. Just in terms of a little bit of jargon, so that if you see this when you're reading papers about this, you'll know what it means. Coherent spin state is just the state of n spins where they're all in a product state in the same one. Okay. And again, let us draw what we had before. Except now, okay, the Bloch sphere doesn't actually look bigger, but let's imagine that now, the length of this, this is sort of, n over 2. There's n spins instead of 1. Let's imagine that again, we have some collective coherent spin state, and that state is given by now psi naught is equal to 1 over square root of 2 down plus up. But now all n of my spins are in the same state. And this is, of course, okay, let's pick an axis just to be easy on ourselves. Let's call this x, y, z. So the initial spin state, I've tried my best to align along the x-axis. This just corresponds to the product state along the x-axis. So there's many names for this. You can think about it as the superposition of up plus down tensor n. You can think about it as the product state along x. People call it the coherent spin state along x. All of them represent the exact same thing. And again, let's just follow our nose and try to understand what exactly is associated with this noise. In particular, again, let's imagine that we're trying to sense a magnetic field, and that magnetic field's in the z direction. So in order to acquire a signal, we simply evolve under the unitary corresponding to e to the minus ih prime t. Sorry for the terribly drawn circles. And as usual, that unitary evolution corresponding to the magnetic field, let's say the magnetic field is in the z direction, will lead to a Larmor precession in the xy plane. Last time I drew it to emphasize the fact that there was motion. This time I'm going to draw it more realistically for a sensing experiment. If you're really trying to measure a very, very small magnetic field, then likely what you're going to get from your initial dotted red x state is you're going to get precession to a new state that is still differing by some angle theta, which is equal to the strength of the magnetic field multiplied by time. But it won't be displaced by quite as much as I wrote last time. If it were displaced by that much, you wouldn't be worried about the size of the sensing signal. Okay, so this is a slightly more realistically drawn picture of a sensing situation where all I've done is made the one spin problem and literally multiplied it by a factor of n. I have n spins aligned in the x direction. There's no entanglement whatsoever. I can think of these, as we showed last time in this dual perspective, as n separate one particle experiments or as one single n particle experiment. And it's already obvious here that in order to measure the angle theta, which is our signal that encodes the magnetic field, you need to somehow need to sense how much this collective spin has deflected, right? In order to do that, it's kind of obvious that it's deflecting in the xy plane. It was originally pointed completely along x. So if you want to do that, the thing you're going to try to measure, be very clear, is you're going to have to measure the expectation value of sigma y total, right? And by measuring that expectation value, you will immediately be able to figure out how much has my coherent spin state precessed by. Again, compared to the first Ramsey experiment, all I've done is multiply by a factor of n and try to force us to think a little bit more about what exactly, if we wanted to measure without pushing back with the pi over 2 pulse to the z-axis, if we wanted to measure directly a projection like this, how would we do it? We can now ask ourselves a question. What is the intrinsic limitation to how well I can measure this? Okay. And that answer will be exactly related to this quantum shock noise. What's the intuition that I think many of you must be murmuring to yourselves? The intuition is, well, if you want to know how easy it is during the collective spin has sort of Larmor precessed a little bit. And if you want to know how easy it is to be able to resolve that precession angle, what you should probably compare it to, as you kind of have already figured out, it's always variances, is the variance associated with the measurements of my initial state. The intuition is that we ought to compare to the variance associated of our initial state. Okay? Right? So it's extremely natural to think about it this way. You have an initial state, and if you made measurements on it, for example, of sigma y, you would find some variance. And if you now know that it's deflected by some amount, and you want to measure how much that amount is, you have to compare to what are the fluctuations of just randomly measuring sigma y a bunch of times, and can I resolve the small change of my precession angle with respect to that initial variance of that state? Okay. Where's the variance of my state coming from? Well, that's obvious. I have non-commuting objects. My state is initially an eigenstate of the x direction, and that means that sigma y total will simply give me a random, every single measurement of sigma y will give me either up or down randomly. I'll be sampling exactly from a binomial distribution. And the variance, of course, of the binomial distribution is given by sigma squared equals n p times 1 minus p, where p and 1 minus p are the probabilities of the two outcomes. In this case, since my states are all pointed along the x direction, when I measure sigma y, it's 50-50 whether or not I get up or down. So what that means is that for n spin 1/2 in my state psi naught, which I've written there, the variance delta jy squared is exactly equal to n times a half, which is n over 4. Okay. And again, it's not super important what this number is, just that there is an intrinsic variance associated with your initial state, and measurements of the object that you need to measure to be able to sense the signal, sigma y total. Because there are fluctuations from your initial state, it makes it not so easy to resolve a small change in that object on top of the fluctuations that are already intrinsic to it. Okay? That's the challenge of sensing. Okay? So one very nice way, so that's a particular number, but it turns out it's much, much more helpful to look at things pictorially. And one nice way to visualize this kind of quantum shot noise is oftentimes by using, well, okay, one of the representations is the Husimi Q representation of the state. Has a long name, but is utterly simple. In particular, for the Husimi Q representation, let's define the following ket vectors. Let's define the following states, the following state which is given by theta, phi, and n as some coherent spin state on the Bloch sphere. As some coherent spin state on the Bloch sphere. The challenge of this lecture is it makes me draw lots of Bloch spheres. So you imagine having some collective spin vector where all the spins are aligned along the same direction on the Bloch sphere. So the radius of the Bloch sphere is n over 2 as opposed to 1/2. And let's say that the polar angle's theta. Let's see if I can draw this well enough. Let's say this stretches out this way, and that means that we have an azimuthal angle phi over here, and n is the number of states. And if we wanted to write that out exactly, this would be cosine theta over 2 up plus e to the I phi sine theta over 2 down. And again, all n spins in the same state. So all I've written down here are kets that correspond to coherent spin states parameterized by their polar and azimuthal angles. And now, for any state, for any quantum state rho, I can define the Q representation of that, where you simply ask, what is the projection of the state into this basis of coherent spin states? So it's n plus 1 over 4 pi, a normalization factor, and it's going to be the state, the coherent spin state theta phi n, rho hat, the coherent spin state theta phi n. So it's literally for any particular state, any state that we start with, what exactly is the projection of this? What exactly is the projection of this into the coherent spin state basis? Of course, it's already obvious to all of you that the coherent spin state basis is clearly not orthonormal. And that's why this is going to be a useful representation. In particular, because it kind of allows you to visualize the uncertainty of making a measurement on a particular coherent spin state, like the state psi naught. So, specifically for the state that we've been thinking about as our initial state, let me draw it one more time. Right? We've drawn our initial state many, many times here. If you look at the Husimi Q representation, you'll find that there is kind of overlap with a little Gaussian set of states. So it's almost like, it's hard for me to, hopefully, I'm not sure how good my pictures are, but you can imagine it's the arrow corresponding to the coherent spin state, and you have like a little uncertainty circle at the tip of that arrow, okay? And that uncertainty circle is precisely that if I measured in the plane which is perpendicular to my x. I mean, if I measure x, I know what I'm going to get. I'm going to n over 2. But if I measure sigma y total or sigma z total, I will get a distribution of results coming from the fact that there is projective measurement, so there's quantum uncertainty. And the width of that is going to be exactly what this QCME function is trying to parameterize. Okay? And the point at some level is very, very simple. The point is that when I evolve in order to acquire my signal, which is the small rotation angle, which is the small rotation angle, which is the small rotation angle. Let me try to draw like this, which is the small rotation angle theta that corresponds to the Larmor precession that my spins have accumulated. If that angle is smaller than the width associated with this projection noise, then it's very, very hard to be able to sense that small change. So if the width is greater than theta, then that makes it hard to resolve the signal. Hard to resolve the signal. And this object here, at least this pictorial representation of the object, is what we call the quantum projection noise. It is the randomness associated with making a projective quantum measurement. Okay. Is that clear to everyone? Okay, at least what I'm trying to get across. Right. So initially, in the first lecture, we really emphasized just from pure estimation theory, what are the bounds for how well your variance can change as a function of the number of measurements that you take? What's your resolving power of the change of a signal? Right? And here I'm emphasizing that, indeed, as per the question that was asked, there are many, many sources of error or fluctuations in an experiment, in a sensing measurement, that may be governed by classical things. There are also things that are governed more by the actions of quantum mechanics, and the thing that's intrinsic to that, one example is the quantum projection noise. And the quantum projection noise corresponds to the fact that we measure a signal, there is some stochasticity inherent to the fact that I'm making a projective measurement. And if that randomness is larger than the signal that I'm trying to resolve, then I have a challenge. Okay. Good. So let us introduce what will be called our second shining example of another form of entanglement that allows one to do better than the classical Kramer-Rao bound would. Now I'm going to introduce this notion of spin squeezing as a way to overcome, the quantum projection noise limit that we just talked about. And this is going to be our example number 2 of a type of entanglement, of a particular type of entanglement that allows one to beat the classical Kramer-Rao bound, at least assuming that there are no classical noise sources that are otherwise limiting you. And of course, as promised, the end of the lecture really focus on trying to find some unifying way to understand all of this together. Okay. Good. So let us again start by considering the state that we've just been talking about. Psi 0 is equal to the product state along the x direction. And now let's just look at the quantum projection noise in the YZ plane. We've already emphasized that there really is no noise in the x direction because we are an eigenstate of the x direction. But if we made any measurements on the operator sigma y total, sigma z total, or any linear combination cosine theta y plus sine theta z, you would find a uncertainty bubble that you could represent using the Husimi-Q representation. And again, drawing, now you could have to imagine this arrow is coming from deep inside the block sphere in the third direction. So that's initially where it is. And I've said before that if the final state, if your initial state psi naught looks like this, and our final state psi theta is not so well resolved, then it will be hard. And we can ask ourselves, what are some natural ways, natural strategies to be able to make this sensing better? How can you do better? Well, the obvious one is, can we make the quantum projection noise smaller? What do people think about that? What if I could somehow shrink the red bubble, of course, to be smaller and smaller? That would certainly help, right? What do people think about that strategy? Is that a viable strategy, yes or no, and why? I'm trying to look at you guys. I can't really see all of you. I see someone who's, I don't know if you're scratching or on the raising your hand, but I saw some motion of some arm. Just call out. Go for it.
No.
Yeah, so the answer is no, yeah, okay, yes. And why is this not a viable strategy, my dear friend?
Uncertainty principle.
Yes, the uncertainty principle, exactly. So it turns out the coherent spin state already satisfies the uncertainty principle. In particular, the uncertainty principle tells us that delta Sy, delta Sz must be greater than or equal to 1/2 the norm of delta S, which is equal to n/4. And we had just learned a little while earlier that indeed the variance of the state coming from the binomial distribution is exactly given by n/4. So that's not a viable strategy. The viable strategy, on the other hand, instead, is to try to reshape the quantum projection noise, again, up to limits imposed by Heisenberg uncertainty. Uncertainty. Exactly. Very good. And the idea is that if, again, my signal is still the same size, so I have some initial psi naught, excuse me, and some final psi theta, and I'm trying to resolve, as with all good sensing experiments, they can almost always be thought in terms of Ramsey. I'm trying to resolve my Ramsey angle theta. If I could somehow Heisenberg uncertainty constrains the overall area within this uncertainty bubble. But if I could somehow reshape it such that it's long along one side, but short along the axis that I'm actually interested in measuring to be able to discern the signal, that would be a way to somehow try to overcome this limit imposed by the quantum projection noise. This type of state that has this very elliptically shaped Q function or spin projection noise or quantum projection noise is precisely what we mean when we talk about a spin squeeze state or when you hear the words spin squeezing in the literature. Okay. The obvious question, we probably wouldn't be here if it wasn't true, but you can ask, can one achieve this? Is this type of a state realizable? The answer is yes. And in particular, we will now explore a very nice discussion of how to realize this from a paper now, I guess 30 some odd years ago, by Kitagawa and Ueda in 1993. Again, I apologize to the spin squeezing experts in the audience, but I hope everyone's following. And feel free, as I've said before many times, please call out with questions. I won't stop always to ask for questions, but please call out. The example that Kitagawa and Ueda considered is the following model system or Hamiltonian. The following model system or Hamiltonian. and it is colloquially known as one-axis twisting. One-axis twisting, or oftentimes just called the OAT model. It is a Hamiltonian for n spin 1/2, and the Hamiltonian HOAT is given by 1 over n sum over ij sigma zi sigma zj. It's about the simplest Hamiltonian one can imagine. And for those of you guys from a slightly more condensed matter background, this can well be called the one-axis twisting model, which it is in the quantum metrology community, but it's obviously also just an all-to-all coupled Ising model, right? Ising referring to the fact that the interaction between the spins is kind of density form of sigma z, sigma z. And of course, this Hamiltonian is very naturally rewritten in terms of the kind of total spin operators that we've come to know and love. In particular, with our sigma z total as previously defined as just the sum of each of the individual sigma i's. This is simply equal to sigma z total squared divided by n. Oh, I think I missed a factor of 4 probably. That's fine. Okay, so now just zooming into a particular scenario. So the logical flow has been that we defined bounds on variances of estimators when we try to do parameter estimation, which is what a sensing measurement is. We've emphasized that sometimes, in certain cases, those variances can be helped by quantum mechanics. And the first thing we're trying to unpack here is an example of how quantum mechanics limits things by yielding a spin or quantum projection noise. And spin squeezing is going to be an entanglement-based strategy to be able to overcome that limit. Good. So one thing I wanted us just to note is that there are many experiments demonstrating this type of OAT model in beautiful atomic physics experiments, mostly in the context of cavity QED type experiments, where one has, for example, an optical cavity with an ensemble of atoms inside. The atoms barely talk to each other, but they all interact with the cavity mode. And then one integrates out the cavity mode, for example, by keeping it somewhat detuned, to be able to generate effectively all-to-all interactions between the atom pairs. Okay? It's one strategy for realizing this type of an OAT model that many groups, the Kasevich group at Stanford, Schleier-Smith group at Stanford, the Vulicich group at MIT, that many groups have had success with. I should emphasize that in those experiments, there's been beautiful demonstrations of spin squeezing, but I think it's probably also reasonable to say that at least in terms of spin squeezing, this particular type of entanglement, although it has been demonstrated in many different experiments, it has not really been utilized to measure an external signal better than would be possible otherwise. So the entanglement's demonstrated, but whether or not it's been harnessed for actually doing quantum enhanced metrology, that's probably not yet the case. Good. So within the context of the example, I can offer a very simple claim. And my claim is the following: that in fact, starting with this initial state, which is again equal to product state along the x direction, starting with my initial coherent spin state along the x direction, I claim the following: that if you simply evolve with the OAT Hamiltonian as has been defined above, that you will generate a squeezed state. Generate a spin squeezed state. Now, I should emphasize there's multiple pieces of evolution here. Step 2 of the general quantum sensing protocol also involved evolution under a unitary to pick up your signal. This is not that unitary. This is the preparation of an entangled state that will make the precision, the sensitivity of which I can achieve in my quantum sensing experiment better. Okay? So these are not the same unitaries. Okay? You have a very, very simple proof by kind of pictures. And that proof just proceeds by first noting, as you all note from your quantum mechanics textbook, that the way we generate rotations around, for example, sigma z total, is via the unitary evolution e to the I theta sigma z total. Right? So if we had our collective spin and we wanted to perform a rotation, I think probably by theta over 2 or 2 theta here, around sigma z, you would do so by applying the unitary e to the I theta sigma z total. And in this case, if we simply look at our evolution e to the IHOAT times time, that equals e to the minus I over n sigma z total times time. And all I've done completely trivially is just to break down my sigma z total squared into 2 factors of sigma z total. But these 2 factors sigma z written out this way kind of give a little bit of an intuition for what this particular unitary does. And in particular, the unitary implements, it takes my coherent spin state and implements a rotation around z, down the z-axis, by an angle that is proportional to the value of sigma z total. Okay? Implements a rotation around z, but an angle proportional to the value of sigma z total. And the powerful thing that one can now do is to ask ourselves, okay, how, now that we have this intuition, how does the quantum projection noise evolve under this unitary that's equal to e to the IHOAT times time, right? How does our quantum projection noise evolve under this? Indeed, our goal is that the pressure noise has to change. If it's not changing at all, then we know that we still have our initial circular distribution, but we want it to somehow get reshaped and to be squeezed along at least some axis so that measurements that correspond to distinctions of deviations along that small axis will be easier to resolve. So let's draw a picture, as I promised. There'll be a picture for how to think about this. So again, kind of using our cartoon Husimi Q representation of the projection noise. Again, just to be super, super clear, you know, all we're really saying is something very, very obvious, that if for the product X state, you measured sigma z, most of the time you'd get measurements that are centered near 0, but sometimes you get measurements out here, out here, out here. And that's what we mean when we say that there's fluctuations and noise. Same thing along Y. Most of the time you get measurements here and here and here, but sometimes you get measurements out here, out here. And again, for any axis, cos theta y sine theta z, you could draw the same thing. Most you get over here, but sometimes a couple of times you get out here, a couple of times you get out here. And so I just wanted really to make absolutely sure that it's clear kind of intuitively what we're drawing by this. Okay. But again, with the picture that we're implementing rotations, the evolution of HOAT is to implement rotation around Z, but angle proportional to the value of sigma Z total. If we take this point, this topmost point, associated with a quantum projection noise, then and say, let's just say by convention that it gets rotated to the right by a certain amount, then this bottommost point, which has sigma Z total being negative, must get rotated to the left because the angle theta corresponds to negative sigma Z total. Points here get rotated a little bit less because they're still to the right because they're above zero, but a little bit less because they're not as large as the largest value of sigma Z total. And points here a little bit to the left because they're not as small or not as negative as the most negative value of sigma Z total. And now you can kind of see that if you try to redraw the shape that emerges in this case, you can naturally imagine that indeed what happens is that this initially circular spin projection noise becomes squeezed into an ellipse. Okay. And this is true. And this is true. Evolution under HOAT literally shears the original symmetric quantum projection noise into an ellipse. Super, super cool. This ellipse is oriented at a weird angle, and I should just very quickly comment to get us back to the kind of elliptical situation that I mentioned earlier. All one needs to do is to perform a global rotation by an angle theta g around the x-axis. So it does not require anything at the level of controlling single degrees of freedom. It's very easy. All you need to do is to form a global rotation around x by an angle corresponding to theta g. Is everyone clear on this kind of beautiful example from Kitagawa and Ueda of one-axis twisting generating a squeezed state of the projection noise? Okay. Excellent, excellent, excellent. It's always hard to tell when I'm lecturing on Zoom whether people are getting it, so I'll have to ask Francisco as my spy later on to figure out how much people have learned. Good. Okay, so with the having defined this particular strategy for realizing this type of a state, let us now quickly talk about some of the properties of the squeezed state that is generated by this one-axis twisting Hamiltonian. And there, at least this particular version of this, the Wineland squeezing parameter, is from a paper by Dave Wineland in Puree in 94. So the figure of merit associated with how well my squeezing has been performed is oftentimes called the Wineland squeezing parameter, and it's given by c squared is equal to the minimum, I'll write this down first, variance of sigma total divided by sigma x total squared. Okay, so let me break this down a little bit. Clearly, from the entire example of Ramsey spectroscopy, you can think about the figure of merit of how much one wins in Ramsey. how much one wins in Ramsey spectroscopy. Okay? So clearly, there are kind of two things that have to enter. We've already seen one of them. Our emphasis on the spin projection noise already tells us that we want to know what is the minimum variance in this plane that's given by the YZ plane, as is drawn here. Hence, perpendicular means, this means perpendicular to my initial coherent spin state. And this corresponds to the length of my coherent spin state. And the idea is very simple. You want the numerator, you want to have the minimum variance because you want to have a small variance in the YZ plane. You want there in the numerator to be the smallest possible variance in the YZ plane. And again, as I said before, as long as that exists somewhere, I can always just do a global rotation such that my Larmor precession signal is along the direction that has the small variance. So as long as it exists somewhere in the plane, I'm good. And the second, the fact that the denominator you don't want the denominator too small, is that if the length of the collective spin gets too short, you cannot do Ramsey, period. Right? I mean, you're trying to look at the change in the pointing direction of a collective spin vector. If the overall length of that spin vector shrinks, that means my Bloch sphere is getting smaller and smaller and smaller. So if I'm depolarizing all of my polarization in my coherent spin state, then it gets harder and harder and harder to resolve a small precession of that particular operator. So it should already be obvious, but I'll say it just for the sake of saying it, that C squared small is good. Okay? C squared getting small is good. The smaller the C squared, the better your resolving power, the better the metrological power of your state. So I'll tell you some facts about the OAT model. In particular, it turns out that for any system size n, there is an optimal stopping time T optimum, which yields the best C squared optimum. So your figure of merit for squeezing, or how much one wins in Ramsey spectroscopy from a squeezing, does not keep getting better and better and better under time evolution for HOAT. It gets to a best and then gets worse. And this is because of the curvature of the Bloch sphere. And the idea is that if it were really a plane, if this YZ were really a plane and it weren't living on a sphere, then actually it would get better and better and better. You would shear and shear and shear, and the ellipse would get thinner and thinner and thinner along one particular axis. But because the Bloch sphere has curvature, as this shearing happens, at some point it starts to curve around the Bloch sphere. And as it starts to curve around the Bloch sphere, the collective spin vector, which lives in the denominator of C squared, starts to get a little bit smaller. And that getting smaller ultimately leads to a limit on the time, which is the optimal time for spin squeezing. Okay. So because of the curvature of the Bloch sphere, at some point, the denominator starts to get smaller. And that's what hurts spin squeezing. It turns out that this optimum time scales as a function of the number of degrees of freedom as n to the 1/3. And it corresponds, this is an important one, to a c squared, an optimal squeezing parameter that scales as 1 over n to the 2/3. And this corresponds to a standard deviation of the estimator, of the best estimator for angle theta, scaling as 1 over n to the 5/6. I should note that I had to make a choice here. I like to think in terms of variances. Kramer-Rao bounds are in terms of variances for me, but all of the literature on spin squeezies in terms of standard deviations. So it's just a square root between the two, but it annoys me. But we're going to switch to standard deviations for now. Let us recall for just a second that the classical Kramer-Rao bound, or the standard quantum limit, would only ever allow us to have a standard deviation of the estimator that scales as 1 over the square root of n, so 1 over n to the 1/2. The quantum Kramer-Rao bound, which we saw in the Heisenberg, in the GHZ case, which is oftentimes called the Heisenberg limit, in principle says that we can get as good a standard deviation of the estimator scaling with the number of particles as 1 over n. And so what you can tell is that what we have here is that the optimal spin squeezing generated by the OAT model allows one to do better than, to achieve a scaling better than the classical scaling, but not in principle as good as the optimal quantum Kramer-Rao bound allows for. Okay. I should emphasize that this is not a knock on squeezing. It just happens to be a consequence of this particular OAT-based approach to realizing spin squeezing. So there are, nota bene, there of course are squeezed states that saturate the 1 over n scaling. 1 over n scaling. One of the most well-known examples is evolution under a Hamiltonian known as two-axis twisting. Again, just a little bit of jargon in case you guys want to look up that particular model. Okay. Now I'm going to draw a particularly instructive plot, I think, which really forces us to reckon with the fact that note very well that the squeezing parameter is not a proxy for the Fisher information. This is really, really important and something that took me a while. I'm not sure you'll feel it in your bones immediately, but it took me a while to really feel. Which is what that means is that there are kind of different types of metrological gain. There are different types of metrological gain that are not equivalent to each other. And the quantum Fisher information is really the thing. The quantum Fisher information is defined as optimizing over all possible measurements, right? So the quantum Fisher information is kind of the kind of, I don't know what it is the sum of all of them, not the sum, it's the having a hard time finding the right word. But the quantum Fisher information, different types of measurable again, quantum Fisher information, kind of characterizes the metrology in the best case. Characterizes, let me write it this way. Characterizes the metrological utility, assuming all possible, again, measurements. And I will unpack that statement in just 1 second. Okay. In particular, I'll unpack that by, again, I really like this next plot. And I don't know if this is the way that people necessarily think about it. But I'll unpack that by, let us track together. If we computed, starting from the initial state, right? So let us compute the following protocol. We start from the initial state, and then we're just going to time evolve under HOAT. That's literally the protocol that we've been analyzing together. And let's plot 1 over c squared and the quantum Fisher information. Let's do it in 2 different colors. Okay. Again, c squared getting small is good. I want to draw something, but so c squared getting small is good. The quantum Fisher information getting large is good. But I want to draw something on the plot which looks like at least it is the same direction for where both curves are going. So I'm going to draw 1 over c squared. So let's imagine that for a particular system size n, we do this. What you'll find is that, as promised, this squeezing parameter goes up, gets to an optimum. The optimum happens at a time scale that would scale as n to the 1/3. But the quantum Fisher information continues to improve, in fact. And continues to improve. And I think this, you can imagine, gets to this kind of plateau value at a time scale that scales like the square root of n, and to a value that's even higher at something that scales as n. And here, I really have tried to normalize them together. So let me call this the kind of normalized properly. So this is kind of normalized properly. So when the red curve is above the black curve, it means that the state is becoming more metrologically useful. So you look at this plot and you say, Norm, what's going on? Why have you emphasized this thing called spin squeezing to us? It seems like it gets worse at a time scale that goes as n to the 1/3, but the Fisher information, which really is the true thing that characterizes the most general sense in which a state is metrologically useful, keeps getting better and better. Aren't we simply losing out on being able to use that? The answer is yes, but his different types enters extremely hard here. It turns out that generically, for the states that are realized in this time window after squeezing has already kind of gone away, it turns out those states truly have more general metrological utility than spin squeezing, but it is extremely hard, but very hard to use that metrological utility. but it is very hard to use that metrological utility. And what I mean by that is if you took a state that you generated from that intermediate time scale, acquired a signal with that state that you wanted to measure, and then tried to extract that signal, that extraction process can be extremely hard. And in the most general of cases, it requires you being able to backwards evolve using the same protocol that you prepared your starting state. And without the ability to backwards evolve, you could not extract that signal. So now different types really enters extremely hard here. I mean, different types of metrological gain, not just in terms of the structure of the entanglement, but in terms of how useful and how easily usable this entanglement actually is. So here, the point is that this type of a squeeze state, I'm running out of territory. This type of a squeeze state, maybe change the color. This type of a squeeze state, its metrological gain can be used / read out relatively easily. All you need are just global measurements that you would kind of need otherwise. We can go into even more detail about the nuances here, but this is a very, very important point that I wanted to make. Okay. All right. Are there any questions at this point?
Does a two-axis twisting fits with the uncertainty principle?
Sorry, can you say that one more time? I couldn't hear you. Just one more time.
How does two-axis twisting fit with the uncertainty principle?
How does two-axis twisting fix the uncertainty principle?
Fits.
It doesn't beat, it doesn't beat the uncertainty. It does not beat the uncertainty principle. It just, in this case, you're not, the one axis twisting is not limited by the uncertainty principle. It's not limited by sort of it's not limited by the area. It's just limited by the rate of shearing relative to the rate of wrapping. Is that clear? Good. Okay, fantastic. All right, so let us continue forth. So here, let us try to think about, what I would like to think about as a little bit of a universal set of principles for generating, or for, let's call it a little bit more provocatively, predicting metrologically useful states. And as I've emphasized before, that universal principle will be based on a concept called spontaneous symmetry breaking. So thus far, we've seen two kind of what we've called shining examples of entangled states that allow us to beat the classical Kramer-Rao bound. We've seen the GHZ state, and we've seen the spin squeezed state. And I should emphasize that I hope the feeling that you've gotten from going through these exercises is that they're kind of very constructed in some way. They're very constructed in some way. The first, I was trying to look for objects that have maximum superpositions of eigenstates and minimum superposition of eigenstates to be able to try to maximize a variance. And the second, I was really trying to look at how dynamics and Hamiltonian evolution can shear the quantum projection noise of a coherent spin state. Doesn't breed confidence that there is a very simple general guiding principle that unifies these two different states. And for many years, I thought that was not the case. But indeed, this next piece of the lectures is going to touch on the goal that has started out promising, which is that we're going to try to find some framework for predicting and also classifying metrologically useful entanglement. To do so, I need to start with a little bit of an aside. Okay, a little bit of an aside, which is a story about order. A story about what interacting systems of spins, I mean, could be particles, I mean, you can use spins for now because it's been what we're talking about. Sort of what interacting systems of spins want to do at low temperatures. Okay? And it turns out this story, as I'm sure many of you who've taken a slightly advanced statistical mechanics or condensed matter class know, is that oftentimes these spins like to order. And what do we mean by order? Well, the usual story goes as follows. We imagine that we have some Hamiltonian that describes this interacting system of spins. And we enumerate the symmetries of the Hamiltonian. Write down the symmetries of the Hamiltonian. These are operations that, when acted on, do not change the Hamiltonian. So for example, U, H, U dagger equals H. And it turns out the story, the lore of spontaneous symmetry breaking is very, very simple, actually. It says that it's possible for the system to exhibit a state that has a smaller symmetry than its parent Hamiltonian. A smaller symmetry than its parent Hamiltonian. So this is going to be a Hamiltonian or a particular type of ordering that comes up multiple times. But let's just take a very, very classic example that, again, I think many of you will be very familiar with, which is the transverse field Ising model. Let's kind of make life easy for ourselves so that we don't need to worry about zero temperature or finite temperature stuff. So let's work in dimension d equals 2. Okay. So the Hamiltonian, let's consider to be the ferromagnetic case with a minus sign in front. Minus j, sigma zi, sigma zj, nearest neighbor interactions. Minus h, sigma xi. Okay. Again, this is going to be a little bit of an aside, but I promise this has been thought out very carefully. It'll connect to the first lecture very soon. Okay. But at the moment, I'm just telling you what seems to be a wholly different story about interacting systems of spins and what they want to do at low temperature. The story, you're certainly familiar with the word order. Maybe some of you are slightly less familiar with the notion of spontaneous symmetry breaking, but it's really just a framework for thinking about how things order. And that framework says that if we look at a system and consider the symmetries of that system, it is possible that at low temperature, the system favors a state that has a smaller symmetry than its parent Hamiltonian. In this particular example, an obvious symmetry is a rotation by 180 degrees around Z. If I rotate by 180 degrees each spin around Z, a spin pointed in the X direction doesn't rotate at all. A spin pointed in the Z direction becomes negative Z, but because there are two of those, that negative sign cancels. So the Hamiltonian remains invariant under rotations by 180 degrees around the Z axis. And of course, you'll also note that it turns out that in the limit where the norm of J is larger than the magnitude of H, then we are typically in what we call the ferromagnetic regime, or the ferromagnetic phase of this transverse field Ising Hamiltonian. And that means that the spins favor appeasing their interaction energy as opposed to the transverse magnetic field H. And this means that they will want to be at sufficiently low temperatures, more or less either oriented in the all down state or the all up state. Okay. And in the language of spontaneous symmetry breaking, again, it turns out that I won't use that language all that much, but it is the right language. And so if people want to think about it and learn about it, it is the language I will use in this lecture for now. But you can see that if I look at either of these states, if I look at either of these particular states, they are not invariant under rotation by 180 degree. One rotation takes one to the other and vice versa. And that's precisely the sense in which we say that the ground state of the ferromagnet breaks the 180 degree rotation symmetry of its parent Hamiltonian. Okay. Good. Is this clear to everyone as a little bit of an aside? All right, let me think about what the most logical next step. So it turns out, of course, that this order, this type of order, can be diagnosed by an order parameter. And perhaps in this case, the simplest order parameter, again, we're doing a little bit of an example, the simplest order parameter that you can imagine is just the overall magnetization. It's the magnetization in the z direction, let's say mz, which is equal to the sum of sigma zi. Right? And if that has a non-zero value, we expect that we are in the ferromagnet. It turns out that one diagnostic of order, another diagnostic of order, is to look at the so-called connected correlation function of the spins. And this makes even a little bit more sense in terms of order, and magnetization simple, but the connected correlation function of this order parameter precisely tells you how the spins are correlated with each other. Are they aligned with or not with each other? And this becomes particularly powerful. So the connected correlation function in this particular case is going to be, look at this, the sum over ij sigma zi sigma zj. But let's say that we're really interested in just the correlations that are not associated with the fact that what the spins are behaving like individually. And that's what we mean by the connected piece of the correlation function. The connected correlation is exactly subtracting off. It's the sum over ij of sigma zi sigma zj minus the expectation value of sigma zi, expectation value of sigma zj individually. Okay. And here is where the connection becomes obvious. Here is where you start to see a connection to the first lecture. Can anyone point out what this object already kind of looks like? Can anyone point out what this object already looks like? Just yell it out. If there's one word I've emphasized, what have I emphasized?
Variance.
Variance. There you go. So let's go back a little bit. Oh, a long bit. So this somehow doesn't look all that different from caring about the maximum quantum Fisher information is really related to 4 times the variance of the object M in the state row. And here we've taken the variance of the magnetization or of the order parameter. Okay? So it turns out there is, it's actually extremely obvious and mathematically completely rigorous. So it turns out that for pure quantum states, there is a 1-to-1 relation between order, that's in the sense of spontaneous symmetry breaking, and the scaling of the quantum Fisher information, or of the Fisher information. Okay? So it turns out one can show the following very, very nice table, which is that, let's say we have a table where on the left-hand side of the table, I'm going to talk about order. And on the right-hand table, I'm going to talk about the scaling of the QFI associated with the order parameter. Okay? So we say, in the context of symmetry breaking, that when there is long-range order, and now I'm going to define this as when the connected correlation function goes to, at large distances, a plateau value. When the connected correlation function goes to a large distances, the plateau value, the QFI, it turns out you can show scales as n squared. Correspondingly, when there is no order, and here I mean the connected correlation function decays to 0 exponentially quickly. Then the QFI scales with n. This is consistent with the saturating quantum Kramer-Rao. And this is, of course, just what you would naturally get for classical Kramer-Rao. I should emphasize to those of you who are actually very used to thinking about correlation functions and order parameters and things like that, that most of the time we don't actually think about connected correlation functions. At least when Professor Demler taught me how to think about order, I was more thinking about disconnected correlation functions. But it will be clear in just a little bit why this connection to QFI is really in the context of the connected correlation function. And that is because the connected correlation function is really, in some sense, a diagnostic of the cat state nature of the state. And one way to think about why, in the context of symmetry breaking, there's naturally a notion of a cat state is, again, to go back to this very, very simple example of the ferromagnet, where because there is symmetry breaking, there are multiple nearly degenerate ground states, and you can always think about making cat states of those ground states. And if you do make a cat state of those ground states, then that's when the connected correlation function does not decay to zero at large distances. The connected correlation of any one of those product states of the all down or the all up state, that will go to zero. So the fact that we're talking about plateaus exactly implies cattiness, and that cattiness, of course, is also the same sense in which you get metrological utility. So the essence of this table is really related to that. But I'll show that this idea has a little bit more power than that. So at some level, at the level of writing down this table, I think about it a little bit as there being two ideas that are both connected to cat states that happen to go under different names in different communities. But the next set of ideas will use this to give a much more general framework for things. There is an intermediate case that I'll just mention briefly, which is the case of algebraic long-range order. I won't go into much detail here. You'll have to read about that yourself. In this intermediate case, it turns out the quantum Fisher information cannot ever scale as good as n squared, but can, in principle, scale better than n. So, what is the take-home message from this table? So, what is the take-home message from this table? What is the take-home message from the table? What is the take-home message from the table? Take-home message from the table is that if, it's very simple, just look at this first row. It's all encoded here. If one can generate a pure state with long-range order, precisely in the sense that the connected correlation function goes to a plateau, then such a state must be metrologically useful in the sense that it beats the classical Kramer-Rao bound and saturates the quantum Kramer-Rao bound. Okay. So the take-home message from the table is the following: that if one can generate a pure state with long-range order, then such a state must be metrologically useful in the sense that it beats the classical Kramer-Rao bound in terms of scaling with the number of degrees of freedom and saturates the quantum Kramer-Rao bound. There are a couple of obvious caveats. One, it may not be easy. It may not be easy to generate such a state. Two, even, again, it's a point I've emphasized before, even if one does generate such a state. Even if one does generate such a state, it may be difficult to use it, i.e., to read out a sensing signal from it. It's a point I emphasize when comparing the squeezing parameter to the QFI. Actually, let me just quickly ask a question. Hossein, I mean, I could use a lot more time, but I probably would, if it's possible, I probably would benefit from maybe another 10 or 15 minutes to just finish things off. Would that be okay?
Let you know.
Sorry. Say that one more time.
10 minutes is perfectly fine.
Okay, fantastic. Excellent. Wonderful. Okay, good.
If there is no, I think Eugene is giving his first lecture after you, so.
I see. Good. Okay, so I as long as I have the blessing of Professor Demler, then things are okay. Okay, good. Okay, fantastic. Okay, good. I'll try to end quickly. I realize my lectures have been long. Okay. So these are two caveats that one has to immediately think of. It may not be easy to generate such a state, and even if one does generate such a state, it may be difficult to be able to use it, e.g., to read out a sensing signal from it. Let us try together to tackle the first. What is there any universal strategy based on this kind of connection between order and the QFI? Is there any universal strategy based on the connection between order, this connection between order and the QFI, to leverage this notion of symmetry breaking in order to generate metrologically useful quantum states? Okay. And again, I emphasize that here, I mean states that are able to evade the classical Kramer-Rao bound in terms of the scaling of the variance of their estimator. It turns out that the answer to the question is yes, and I will enumerate such a strategy. The strategy, it turns out, is going to be based deeply on this concept of thermalization, or the eigenstate thermalization hypothesis. So this will be very much based on, the intuitions very much based on thermalization. Okay. So the strategy goes as follows. Pick some initial state psi naught, such that, well, okay, maybe let me even start with zeroth one. Maybe I'll have a one. It's better to do this order. Find a Hamiltonian that exhibits finite temperature order. Okay? That means that at a finite temperature, there's ordering in the system. That means that you can get long-range order in the sense that connected correlation functions go to a plateau, and there are states that do so at finite temperature. Okay? Pick an initial state psi naught such that the temperature of this state with respect to the Hamiltonian, temperature of the state is T of psi naught is less than the critical temperature for order. So first you find a temperature that exhibits finite temperature order below some critical temperature Tc. Then you pick some initial state psi naught such that the temperature of the state is T of psi naught below Tc. I should emphasize that for those of you who are very used to thinking about and have taken the lore in about closed systems, here I really mean just that the energy density of the state is lower than the critical energy density. Okay. And then you're done. Because your state is lower than TC, I should say, let me add one very important. Pick an initial state. Ideally, this should be a preparable. It may be that there are no easily preparable such states, but that would be too bad. But ideally, you want to pick a nice experimentally preparable initial state, like a product state would be sweet, such that the temperature of the state is below Tc, or in the thermalization sense, that the energy density of the state is lower than the critical energy density for order. And then you simply time evolve psi naught under the Hamiltonian. And by the connection between order and Q of I, this tells us that at some later time, that state must evolve into one with an entanglement structure, that allows one to saturate the quantum Kramer-Rao bound. Okay. You should feel magicked. It is magical. It's true, but it is magical. As a strategy, everything I've written down is completely true. It turns out that all of the devil is, as usual, in the details, and it is not always very easy to pick a preparable state that is at a sufficiently low energy density in order to be below Tc. That's oftentimes where the name of the game comes into play. Sadly, I have two beautiful examples planned for you, but I'm not going to be able to do them. But I'll kind of do them in ridiculously lightning ways. The first example, it turns out, so let's really test this strategy. Let's test this. Test via examples. In particular, the first example is going to go back to a Hamiltonian that we saw a little while ago. In particular, let's take the example of this 2D transverse field Ising model that we just literally wrote down a little while ago when defining things. Okay. So, again, can someone, and let's say that we're going to be let's work in the ferromagnetic regime. Consider that we are in the parameter regime of the Hamiltonian in the ferromagnetic phase. And as I promised, because we're in 2-dimension, it turns out that there is finite temperature ferromagnetic order for this Hamiltonian. All right, one last test, maybe the last question I'll ask in all of my lectures, but somebody has to answer. Can someone throw out a state, a product state, that is a low temperature relative to the ferromagnetic ordering temperature? Can someone imagine it's not a trick question. Can someone imagine a state that is low temperature relative to the ferromagnetic Tc? So there's some finite Tc. I could wait here forever. Come on. What's a product state that's low temperature in the ferromagnetic phase? All right, I'll for Eugene's sake, I'll say so. Either of the all down or the all up state is clearly fine. So if you start out, it turns out in, let's say, the all down state, that satisfies everything. The Hamiltonian strategy one, the Hamiltonian exhibits final temperature order. You've picked an initial state all down that is below TC for sure. It's nearly the ground state. And you say, oh, this is completely weird. A product state has no entanglement whatsoever, and it can't do anything that useful. And all we know from the third strategy is that now, what if we evolve? What if we evolve under the Hamiltonian H? It turns out that if you recall, I'll draw it down here, the gap at any finite n, it turns out that the eigenspectrum of the ferromagnet looks like the following. There are two very low energy states separated by an order 1 gap to all excited states. And if you went to Mathematica or Python and diagonalized it, you would find at any finite n that the two states here are actually the cat states. There's an exponentially e to the minus n small gap. And the two cat, but the ground states are the two cat states, all down plus all up, and all down minus all up. Okay. Which means that the state that you've chosen here is not actually an eigenstate. And after evolution, eventually this state will pick up a phase. And it'll evolve into, because it is a superposition of these two plus and minus cat states, at some point that phase on one of them will be such that all you're left with is the coherent superposition of, for example, let's say the plus cat. So the strategy absolutely works, except for the fact that the time scale it takes to do so takes an e to the L amount of time to do so. So clearly, even though this is a viable rendition of the strategy, it doesn't allow you to prepare metrologically useful states in a short enough period of time or a sub-exponential amount of time. It turns out that the example that does allow one to do that is, for example, the XY model. In particular, in that model, the Hamiltonian, for example, we can consider negative sum, again, nearest neighbor spins, j, sigma xi, sigma xj, plus sigma yi, sigma yj. This model, again, has now a different easy plane type of ferromagnetism. Let's say we're in 3D. So this has an easy plane ferromagnet with a finite TC. And it turns out if you start with this type of a state, even though the Hamiltonian looks completely different than the one-axis twisting Hamiltonian, if you evolve under the Hamiltonian, you will get a spin squeezed state, tying the full story together and in a polynomial time, much like you have in one-axis twisting anyways. Okay, so with that, I'm happy to answer questions via email and stuff, and also now, but I won't take any more of Eugene's time. Thank you for your attention.
Any sort of comments or question?
I can stop sharing my screen so people can see me.
I have a short question. So is there any advantage of using large spin instead of spin halves and balancing it out with less number of spin particles? Or is it a bad idea?
That's a good question. So let me think about that for a second. Is there an advantage of using, sorry, let me go, but by large spin, so there's maybe two things to say. So by large spin, do you mean, thinking about the spin one halves as a collective spin, or do you mean large spin in terms of literally the degrees of freedom are kind of like qubits, like spin one objects themselves?
I'm thinking about spin one or higher things.
Yeah, that's a good question. I don't, yeah, okay, so it turns out, as you can imagine from the framework that I'm trying to give, you can get slightly different types of symmetry breaking when you get to higher spins. So because you can get slightly different types of symmetry breaking, that means that in principle, you should be able to get different types of order parameters and thus different types of metrologically, like different types of states that can be metrologically sensitive to different things. In terms of whether or not you'd expect that to sense, like, for example, just, a small uniform magnetic field, whether or not n spin one degrees of freedom would be better than n spin 1/2 degrees of freedom. I mean, there's certainly an obvious, there's something to say yes in the sense that the magnetic moment is larger, but there's also larger fluctuations because you have three states that you can get when you have the projective measurement. So I'm actually not sure exactly what the answer is.
Well, yeah, but
I have a question along the same line, so these formalisms that you presented are regarding these qubits, but what about like bosons, scientific bosons or fermions?
Yes, yes, absolutely. So this formalism, absolutely. In terms of thinking about symmetry breaking, and I mean, the formalism completely applies to whether fermions, bosons, other degrees of freedom as well. Although you have to be commensurately, you'll be very careful as well, thinking about, in the end, the sensing protocol has to involve taking the state that you generate, acquire a signal, and reading that out. And that'll, of course, be different depending on the type of particle that you're looking at.
any more questions? If not, Norm, thank you very much for a beautiful lecture. I appreciate it. It looks like you're feeling better. You're back in the office. So that's
Yeah,
an
well,
important.
yesterday there was so much noise from the kids. It was hard to give my lecture yesterday, so I came in today.
Yeah, oh, I see. Okay, excellent. Thank you
Yep.
very
Thanks,
much.
thanks for saying. Thanks so much. Sorry to
Sure.
miss everyone. See you. Bye bye. Bye bye.